Hello everyone. The title of this video is Finding Equations of Exponential Functions. Oops. So in this video, I'm going to be doing examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.1, called Exponential Functions, and I'm under the heading Finding Equations of Exponential Functions. Alright, so each example I'm going to do is either going to be an example from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Okay, so by now you should know what an exponential function is, how it's defined, what it looks like. Should it be any function of this form, f of x equals a, some real number a times b to the x power, right, where b is a positive number that's not 1 and a is non-zero. And know that the function doesn't have to be called f, and the input variable doesn't have to be called x, as we'll see in some examples coming up, but anything of this form is an exponential function. And our goal is basically just going to be, given information, find a and b. If you know the value of a and the value of b, you've got your exponential function. And that usually only requires 2 points on the function. 2 ordered pairs, 2 pairs of inputs and outputs. Okay, and there's a little how-to you can read here, but I'm just going to go over some examples myself. Alright, so this first example says, in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Those are the key words there, so you know you have to model it with an exponential function. Basically growing by the same percentage every year. Whereas to write an exponential function, not f of x, but n of t, representing the population n of deer, so n represents the number of deer at some time t, where I'm assuming t is in years here since they give us year numbers. So we're looking for this. We're looking for n of t equals some number a times, and then some number b to the t power. Or again, t, we'll say t represents now the initial year they gave us was 2006. So I'm going to have t represent the years since 2006. Years that have passed since that year. That first year they gave us, that initial year. And, n of t, right, the output, is just going to be the number of deer at time t, right? I'll just put number of deer in this wildlife refuge. Alright, and then, like I said, we're trying to find, all we need to do to complete the function, to complete the model, is find the value of this a and b. That's all, using the information we were given. Now, reading back through it, we are given 2 pieces of information about inputs and outputs here. The first sentence, in 2006. So 2006 would be when t equals 0, right? The initial time is time 0. There are 0 years since 2006 if you're in 2006. 80 deer were introduced into the wildlife refuge. So this is the number of deer in that refuge when t equals 0. This is n of 0. So we are told, n of 0 is 80, and this will help us find the value of a. And very often a is called the initial value in this exponential equation model. The initial amount of deer. You're going to see that a is 80. Well, let's see it. So I'd have 80 on the left side, right? That's the value of n, equals a times b to the 0 power, right? T is 0, and then n is 80. So the left side is 80, and I replace t with 0. Now, hopefully you recall some properties of exponents. I'm assuming you do. When you have a, b is not 0, right? B should be some positive number. Anything not 0 to the 0 power is 1. So this is just a times 1. So we are seeing the value of a is 80. Right, so now the model looks like this. N of t equals 80 times b to the t power. And now all we have left to do is find the value of b. We found a. A was 80, that initial amount. And this is where the other piece of information will come in. 2012, which is 6 years later, right? So 2012, t equals 6, right? T represents the years since 2006. The population had grown to 180 deer. So that's n of 6, right? That's the number of deer after 6 years. So we're told that n of 6 equals 180. And I can use this to set up an equation to find the value of b. Well, putting in 180 for n, so that's the left side, and I'm putting in 6 for t. So this equals 80 times b to the 6th power. Right. Then I solve for b. Right. So we'd have b to the 6th equals, now 180 divide, we would divide by 80 first. That'd be 18/8 or 9/4, which is 2.25. And then the value of b is the 6th root of that, the principal 6th root, right? I have the 6th power, take the 6th root of both sides. Alright, and if I put this into a calculator, let's go to that Desmos website. Now instead of the 6th root, I will just take 9/4 to the 1/6 power. Alright, that's the 6th root. And we're getting about 1.14471, blah, blah, blah. I'll just go 4 decimal places there. 1.1447. So this is approximately 1.1447 if I round to 4 decimal places. And notice that this b is, that's bigger than 1. And if you recall from an earlier video, that means we have exponential growth, and it should be growth, right? The population of this deer population should be growing. Okay, so now our model looks like this, right? Putting this all together, this is the value of b. We have the value of a is 80. The exponential function I'll be using then is n equals 80 times, and then 1.1447, which was about the 6th root of 9/4, to the t power. Alright, and this, I'll put this in a box. This is what they were asking for. And that's really all you're doing. Right? You know what the model looks like. You know what a basic exponential function looks like. You just need to find the value, that initial value a and the base b, using 2 pieces of information. And you should be given enough information to find these values. Alright. So let's continue on. So I'm doing pretty much the same thing for the rest of these. So yeah, we're asked in the next examples to find the formula, right, for an exponential function that passes through the two given points. So again, we have, I'll do f of x again this time. All right, f of x equals a times b to the x. We'll end up writing an equation like this. I just need to find this a and this b. Now, unfortunately, this time we don't have the initial value. We don't have the value of f when x is 0. We have the value of f when x is 1, and we have the value of f when x is 2. But that's okay. As long as you have 2 bits of information, 2 ordered pairs, 2 points on the graph, you should be able to find a and b by setting up a little system. Right. So the point 1, 3 leads me to the following equation. Right? 3 is the value of f, so I have 3 on the left side. And then, x has a value of 1. So a times b to the 1, or just a times b. So whatever a and b are, a times b has to be 3. All right. And then this point here, right, the point 2 comma 4.5 is on the graph. So 4.5 is the value of f. I'll put that on the left again. We're replacing f of x. F of 2 is 4.5. And then the value of x is 2. Right, so a times b squared. Right, replacing x with 2. Okay. Well, do this a couple ways. What we have here is a system. Two equations with 2 variables. So we're going to solve this system for a and b. Alright, so I could do it with kind of a substitution here if I wished. We have up here a is 3 divided by b. Right? 3 divided by b. And then I substitute, let's put sub, into this equation where we have 4.5 equals a, but I'm replacing a with 3 over b times b squared. And then we see one of the b's canceling. So this is just 3 times b. And then dividing both sides by b, we're seeing that b equals 4.5 divided by 3, which is 3 halves when you reduce, or 1.5 if you want a decimal. It's 1.5. And then if b is 1.5, 3 divided by 1.5, then a is 2. Right. Putting 1.5 in for b here, 3 divided by 1.5 is 2. And that's all we need. I got a is 2, b is 1.5. I know now what the equation looks like. F of x equals 2 times 1.5 to the x power. And that is all they're asking for. Right. And again, if you want to verify it, just make sure that these points belong to this function. Right. If x were 1, 1.5 to the 1 would be 1.5. 2 times 1.5 would be 3. And if x were 2, 1.5 squared would be 2.25, 2.25, times 2 would be 4.5. So this indeed checks out. That is the exponential function we're looking for that has these 2 points on it. And that should be all you need, is 2 points. So let's do that again. Right, so here again I'm given 2 points. I'm trying to set up a function like this, right? F of x equals a times b to the x. And we know the following information, that f of negative 2 is 6. So that gives us this equation, 6 equals a times b to the negative 2 power. All right, replacing x with negative 2 and f of x with 6. And then the other equation in the system, I'm replacing x with 2 and f of x with 1. We get 1 equals a times b squared. Okay, and then again, I'm solving this system. Now, if you recall, b to the negative second is 1 over b squared. So from this equation, I get a equals 6 times b to the 6b squared. Sorry, just multiplying both sides by b squared. And then I substitute this in for a in the other equation. We get 1 equals 6 times b to the 4th. All right. So that leads me to b is the 4th root of 1/6. All right, divide by 6 and take the 4th root. And then if that's the case, then a is the square root, right? Because b is 6 this would be 6 times and then b squared. A is 6 times b squared. This squared would be the square root of 1/6. All right, and actually this just ends up being the square root of 6 if you think about it. This is 6 divided by the square root of 6 basically. Right. So we have f of x equals the square root of 6 times, and then the 4th root of 1/6 to the x power. All right, and if you're having a hard time checking that, well, let me actually punch this stuff in. I'm going to go to the calculator and we'll round these things. First, I'll enter this function the way I have it. I have f of x equals the square root of 6 times, and then I'll put 1/6 to the 1/4 power, right? That's the 4th root of 1/6 to the x. All right, and you see it's an exponential function. It's got that look, a decreasing exponential function. And if I make I say what's f of negative 2, see it's 6, right? Just like they gave us. They said negative 2, 6 was on the graph. And what's f of 2? It's 1, right? And they said 2, 1 was on the graph as well. All right, so that works. That totally works. Now, if you want to put some decimals in, do some rounding, let's see, the square root of 6, it's about 2.4495. And then the 4th root of 1/6 to the 1/4 power is about, and you see how b, right, this was the value of b, this 4th root of 1/6. See how it's less than 1 and we have a decreasing function, right? Exponential decay model. That's what happens when the base is less than 1. Right? It's about 0.6389. Again, I'm just going to 4 decimal places for all these like earlier. So back on my paper, we can say it's approximately this. And f of x is approximately 2.4495 times 0.6389 to the x power. But either one of these is fine. And when you plug in negative 2 for x, you should get 6. Or if you plug in negative 2 here, you'll get something probably really, really close to 6, because these are approximations. And if you plug in 2 for x, you'll get 1 here, or something very, very, very close to 1 here. But again, that's all you need is 2 ordered pairs. 2 points on the graph you should be able to determine an exponential function that models it, that goes through those points. All right, and I've got just a few more of these. It's all the same, really. It really is. All right, so example 4. Now example 4 is a nice one because they do give us an initial value. Right. Initial value happens when the input is 0. Basically the y-intercept, right? Yeah. So again, we have f of x equals a times b to the x, and we can see from this a equals 6. We know right away that a equals 6, because if I replace x with 0, b to the 0 is 1. You're just going to get a equals 6. So now we have this, f of x equals 6 times b to the x, and now we just need to find b using the other point. So output is 750. I'll put that on the left. Replace f of x with 750, and replace x with 3. So equals 6 times b cubed. All right. Let's see. If I divide by 6, 125, right? 6 times 125 would be 750. So 750 divided by 6 is 125. And then now this one has a nice cube root, right? You take the cube root of both sides, that'd be 5. B equals 5, period. No need to round anything. 5 to the third power is 125. So then we're done. We have f of x equals 6 times 5 to the x power. And there's your answer. There's the exponential function that they're looking for. And again, just verify, if you plug in 0, you'd get an output of 6. If you were to plug in 3, 6 times 5 cubed, 6 times 125, you'd get an output of 750. So that indeed does work. That is a valid exponential function with these 2 points on it. Alright, and I just got 2 more like this. That's, again, all you need to find a valid exponential function is 2 points. Alright, so once again, we're doing f of x equals a times b to the x power. Here we're told that 3 halves is the output when -1 is the input. So a times b to the -1. Or a divided by b if you want to write that. Same thing, right? Because remember, b to the negative first is just 1 over b. And then 324, right? So 24 is the output when 3 is the input. So 24 equals a times b cubed. Alright, so from this equation we see that a is 3 halves times b, right, if I multiply both sides by b. And then I'll substitute this for a in the other equation. So now we have 24 equals 3 halves times b to the 4th, right, because you have b cubed there, b there. I would multiply both sides by 2/3, giving me b to the 4th equals 16. So b must be equal to 2. Right. And there we go. We have b is 2, and then I plug that back in here. A is 3. Right. 3 halves times 2 would be 3. And there we go. So f of x equals 3 times 2 to the x. There's the function they want. Right. That has both these ordered. That's an exponential function that has both these points on it. Alright, and again, check it out. Plug in -1 for x, you'll get 1.5 for the output. Plug in 3 for x, to this function, you will get 24 for the output. Alright, and one final one here. So once again, we're looking at f of x equals a times b to the x, going through these 2 points. The point 3,1 is on there, so 1 is the output, 3 is the input. So 1 equals a times b cubed. And then the point 5,4 needs to be on it. So 4 is the output, 5 is the input, so 4 equals a times b to the 5th. Alright, and then just like all the others, I'm going to take the first equation. I'll just solve for a. A equals 1 over b cubed. And dividing both sides by b cubed. substitute this in for a in the second equation, 1 over b cubed times b to the fifth would just be b squared. So b is 2. And again, it could be positive 2 or negative 2, but we want the bases to be positive. I know negative 2 squared is also 4, but positive 2 is the one we're looking for. So b is positive 2, and then plugging that back in here means a is 1/8. All right, 1 over 2 cubed. Yeah, so f of x equals 1/8 times 2 to the x. And there you go. And this satisfies these, right? When you plug in 3, you get 1. 1/8 times 8, that's 1. And when you plug in 5, you'd have 1/8 times 32, 2 to the fifth, that's 4. So that works. Now you could also do something a little more with this, 8 is 2 cubed. And then you have basically 2 to the x divided by 2 cubed, which would be 2 to the x minus 3 power. You could also write it like this. This is equally valid. Right, where I'm using a property of exponents, right? When you divide two things with the same base, you subtract their powers. Numerator power minus denominator power. This would also work, right? If you plugged in 3 for x, you'd get 2 to the 0, which is 1. You plug in 5 for x, you'd get 2 to the second, which is 4. Right? So they're the same function. It's up to you, right? It really doesn't matter. As long as it's exponential, you have a positive numerical base, and then some exponent with a variable, right? Just a variable to the first power. And the ordered pairs that we were given are actually on that function, to satisfy that equation. You should be good. And that's it. Pretty short one. So I'm hoping that watching me go through these 6 examples here help you in some way when you're asked to find an equation for an exponential function, given a couple pieces of information on your own. And thank you very much for watching.